All right, so this is the second video about the derivatives of exponential and logarithmic functions. In this video, what I want to do is take for granted the fact we proved in the previous video that the derivative of e to the x equals e to the x. And then we're going to use that to find some derivatives of other types of functions. To start with, we're going to look at any positive number a greater than 0, a constant. And we're going to see if we can figure out the derivative of a to the power x. We're going to be able to use some properties of logarithms and exponential functions in this video to our advantage. So get ready for a review of those properties. So the first thing we're going to use is the idea that a logarithm and an exponential function with the same base are inverses of each other. In particular, we're going to use the fact that put a little note here. We're going to use the fact that if we do e to the power natural log of a number, no matter what number it is, that it's equal to that number. And the reason is because e and the natural log are both base e, and they are inverses of one another. So when you compose them together like this, they essentially cancel each other out, just the way inverses always do. This is like f of f inverse of a, and that is a. This is a general fact about inverse functions. It's true when you say multiply by 2 and then divide by 2. They cancel out. So you add 5 and then you subtract 5. Those cancel out, right? Same idea. So what that means is we can rewrite this function, a to the power x, as e to the power natural log of a, and then that whole thing to the power x, like so. That's the first. Now the second step, still not doing any derivatives, okay? We're just algebra manipulation. The second step is to use the fact that when you take an exponential expression and raise it to a power, you can multiply the two powers together. So the natural log of a and the x are going to be multiplied together here. So we get e to the power natural log of a times x. All right. Now we're going to try to do the derivative of this, right? And we're going to use this fact here along with the chain rule in this case to do the derivative of this. So we view this overall as like a composition of functions. Here we could say our outer function, this is like y equals f of g of x. So y equals f of u. And that is basically e to the power u, right? E to the power something is our overall function here. And our inner function, u equals g of x, that is going to be the natural log of a times x. Okay. Now the derivative of the outer function is just itself, because that's just this rule, right? That's just this rule that we're using here. So the first thing I'm going to get here is e to the power everything that I had in there before. Right, that's just applying the fact the derivative of e to the u is e to the u. Then we have to do the derivative of this function. So let's just do that by hand over here. What is g prime of x here? Well, this is tricky because it looks on the surface like you might need to know the derivative of a natural logarithm in order to do this, but actually you don't. And the reason is because what's inside the natural logarithm is just a constant, a. And so since there's no variable inside there, we don't need to do any derivative of that part. We take this entire natural log of a, treat that as a constant multiple. So this is no different than, for example, taking the derivative of like 5x. You would just get 5, right? So it's just like really no different than that. So I'm going to say this is the natural log of a. Just a constant multiple of x, so its derivative is a constant multiple times 1. Done. So I'm going to take over here, applying the chain rule now, I'm going to multiply by the derivative of my inner function, which is just the natural log of a. There we go. So I've got the derivative. Now let's massage it back into a format that looks a little nicer. I'm going to do the reverse of the above steps. So the first thing I'm going to do is take this product, natural log of a times x, and I'm going to break that out into a power of a power, right? Then times natural log of a down here. Sorry. wants to save. So there we go. So we have a natural e to the power natural log of a, all of that to the power x, and then times natural log of a. And then we're going to do the reverse of the very first step we did, reverse of this, where this here is just equal to a. So this is a to the power x times natural log of a. And there we go. If I sum that up in another differentiation rule, it looks like this. The derivative of a to the x is itself, but then times the natural log of a. And that, we can use that as a new differentiation rule. That is our generalized differentiation rule for any exponential function. I don't know why this isn't working very well today, folks. I apologize. I think if I use my finger, there we go. Better. So compare that to the original rule that we had, right? Here's the original rule. Here's the general version. If you had a equal to e, this general version still works because the natural log of e is equal to 1. So you'd have e to the x times 1, which is just, back to this again. So in that sense, it really is a generalization. It is a rule that works for any exponential function, including the specific case when your base is equal to e. So it's a rule that encompasses the original one as a part of it. That's what it means. That's what a generalization is. So, all right, moving on. The next thing we want to do is to see if we can figure out the derivative of the inverse of the e to the x function. So here we have, I must have been reflecting my canvas earlier, and I wrote d prime in reverse over there. Sorry. All right, so we want to see if we can figure out the derivative of the natural logarithm. And to do that, we're going to approach this in a slightly different way. Instead of using this operator notation like derivative of natural log of x, this time we're going to write y equals natural log of x, and our goal will be to find the derivative of y with respect to x. It's an equivalent way to write it, just sort of like a slightly different approach. It means the same thing. But this other approach is useful because it means we can take this function this equation involving x and y, and rearrange it. So the first thing we're going to do here is rearrange this equation. In general, if you have like y equals a function of x, you can rearrange it as the inverse function of y equals x. That's always true, and that's again due to this property of inverses. They kind of swap the input and the output, x's and y's, swap places, that sort of thing. So what I'm going to do is I'm going to rewrite this equation as e to the power y equals x, because the e exponential function is the inverse of the natural logarithm function. All right, so now we're going to do implicit differentiation, which is why we've waited until now to do this video. Because we needed to introduce implicit differentiation in order to do this one. So we're going to do the derivative with respect to x on both sides. All right, on the left side, we have e to the power y. So thinking of y as a function of x, we're going to do the derivative of that. But we're going to have to apply the chain rule, right? Since technically this is a composition of functions. The e exponential base e function, and then it's got the y, which is a function of x on the side. So the outer derivative is itself, e to the y. The inner derivative is the derivative of y, which we can just write as dy over dx. Now on the right-hand side, we can write 1, because the derivative of x is 1. So this gives us dy over dx is equal to 1 divided by e to the y. Now that doesn't seem like a terribly great derivative rule, except if you remember back up here, this red, e to the power y equals x. So applying that here, we can actually say this is equal to 1 over x. And there now we have a really nice differentiation rule. So looking back at what we've done, we can now see that if y equals the natural log of x, then the derivative of y with respect to x is 1 over x. And now we can write this differentiation. Great. There we go. Now that is a pretty amazing one. One of the things that's surprising about this differentiation rule is you take this like transcendental function. It's actually called a transcendental function, natural log of x. E to the x and ln of x are called transcendental, as well as other log and exponential functions and other types of functions. They're part of this class. It's sort of beyond algebraic functions that are not just obtainable by like the traditional algebra rules, and beyond that, right? Transcendental function, and you take its derivative and you get a very simple algebraic function, 1 divided by x. And it's kind of surprising, right? It's kind of surprising. If you take something complicated, you take its derivative and it becomes comparatively simple. But that's how it works. And that's pretty cool. So now we're using that rule. We'll then be able to move on to part 3 of this video, which is to again generalize this to not just base e, but any base. We're going to change the base to a, where a is some positive, any positive number you want. Okay, so we're going to find a general version of this formula for log base a. And the tool we're going to use this time is a fact called the change of base formula for logarithms. So log base a can be rewritten in terms of natural logarithms. If we do natural log of x divided by the natural log of a. This is a version of the change of base formula for logarithms that you will have learned in calculus. So we're going to first of all rewrite log base a of x like that. And then I can see that this is in fact just a constant multiple, 1 over the natural log of a constant multiple of this natural log of x function. So in fact, I can apply the constant multiple rule for derivatives and bring the 1 over natural log of a out of the derivative. That times the derivative of the natural log of x. And then I can apply my differentiation rule that I've just established right over here. So this is going to be, the last one was when I used a differentiation rule, it was called, oh no, I didn't do that. So I'm going to use this differentiation rule over here. And we get 1 over the natural log of a times 1 over x. So I'm going to rewrite as 1 divided by x times the natural log of a. I just like to write it with x first. That's the way it's often shown. That way there's no confusion about x actually being inside the logarithm or whatever. It's not. It's multiplied on the outside of the logarithm. So now we can write our last differentiation rule for the day, which looks like this. And this one, again, is a true generalization of the previous one, because if a were to equal e, you would again have natural log of e down there, which equals 1. So it would just be 1 over x times 1. And that's what this says, right? So it truly is a generalization in that it encompasses the previous rule, but it also allows us to do derivatives of other logarithm functions. All right, so that's it for this video. That's the end of the 3 parts. Now we can do the derivative of literally any exponential function and any logarithm function. Pretty cool.